Okay, we come to the last part of the last remote learning before the AP exam is here. Therefore, this is a test. This is not a test. This is a test of your emergency calculus skills. Treat it as such. Two problems. That's right, two problems coming your way just like the real deal, which is not the real deal. It is the COVID 19 alternative deal. Please do each problem and then watch the video. There will not be an assignment. All right, good luck on Tuesday, everybody. Yeah, these problems are really good. I think that they're quite possibly going to be there. The only difference here is that conceptually, I like the problem that I put first rather than second, but the problem first is easier than the problem that is second, and I think it's going to be the other way around on Tuesday only because the first problem is going to have more parts. I do believe you have 25 minutes to do that one and only 15 minutes to do the next one. So it's flipped on this. Keep your eye on the time. You might as well take note of that. But again, I think for the purposes of studying, you shouldn't be timing yourself and getting anxious about that. Okay, so then here is the problem in its entirety. And yeah, go for it. And then come back to the video. Okay, so then we have this function which is defined as the square root of 25 minus x squared, and that's for the interval negative 5 to 5. I happen to recognize that as the upper part of a circle of radius 5. So that's essentially what we got going on. But I don't know that that matters, but I'm taking note of that. And part A is to find f prime. Okay. I'm going to restructure f so that it looks like it's easier to differentiate by writing it as 25 minus x squared to the half power. And now I'm going to find f prime by doing the chain rule here. Okay, so I've got 1/2, and then we have the interior function raised to 1 less of a power by the chain rule times the interior function's derivative, which is negative 2x. Okay, so now I've got f prime is equal to negative x, and then 25 minus x squared to the negative 1/2. Now only that's a good answer, and you could leave it like that and get away with it. But because the problem started out in its square root notation, I'm going to go ahead and put things back into square root notation. And it's a negative power, so it comes down below. Okay, so there you go. That is my f prime of x. Done. Part A is over. Part B, we're going to need more room for that, that's for sure. Okay, so let's go down here and do part B. What does it ask us to do? Write an equation of the line tangent to the graph of f at x equals negative 3. Okay, write the equation of a line. Then I need that line's slope, which is to say I need to know its derivative at x equals negative 3. I'm just writing it like that to remind you, change in y, change in x, that's the slope. Or if you prefer, I need f prime at negative 3, which I can easily go get. And that is negative 3, so that's positive 3 over, and then when I'm putting negative 3 here, it gets squared for 9. 25 minus 9 is 16, and rooted is 4. Okay, so that's one thing I need. I also need a point on the function, the point of tangency, and that point is the point x f at x. Okay, so then I've got -3, and I need to go find f at x. So f at x just got scrolled off the top there, but I can come up here and put in -3, and that becomes -3 squared is 9, 25 minus 9 is 16, root is 4. So there you go. And putting this all together in point slope form, I've got y minus 4 equals 3/4 times x minus -3. And just writing it out nicely, and then I'll stop here. That's 3/4 x plus 3 plus 4. Okay, that is my answer to B. Write an equation of the line tangent to the graph of f at a particular point. So I needed to know the derivative at that point, and I needed to know the point of tangency. Okay, cool. Moving on to C here, where things get a little more intense, I have to say. Okay, so in part C, they give us a function g, which is this piecewise defined function, where on the piece from -5 to 3, we're on that semicircle up above I mentioned on f of x. But then from -3 to 5, we are on some line. Okay, and so that's the piecewise to function g. And then the question is g continuous at x equals -3? Use the definition of continuity to explain your answer. Okay, so that's been a while. So let's remind you about continuity. The concept of continuity is that the function is unbroken, that you can draw the function without lifting up your pencil. It doesn't necessarily have to be smooth. It can be jagged. So don't get this confused with differentiability, where it has to be smooth and continuous. But for continuity, it just needs to be unbroken. Okay, so to find continuity at a point, here's what you need. So this is essentially the definition. Continuity at a point. Okay, so you need the function at that point must exist. So there needs to be, in this case, there needs to be a g at -3. Okay, also the limit as we approach -3 on the function must exist. And third, this value, which I really should say, let's change it. That's since I started putting numbers in here later, let's just go and put in numbers in the beginning. So let me change it to g at -3 must exist. The limit as I approach -3 on my function must exist. And those two things must be the same. So the value that you get when you put in -3 and the value that you get when you run the limit, those have to be the same. Okay, so that's what it takes for continuity at a point. All right, I'm not going to say any more to that, but if you want me to talk more about that, then you can pop into a meet or send me an email. Okay, so let's roll through these things in this case. So let's see, does g at -3 exist? Well, in order to find g at -3, I got to come up here and decide which one of these pieces I'm on. I'm on the top piece. So g at -3 is f at -3, and we found f at -3 just a moment ago. That's 4, so that one exists. Check. All right, now the limit as we approach -3 is tricky because -3 is the very place where the pieces are separated. Okay, so then what they've done here is they've then made you think through a second set of logical arguments, and that is this, that in order to have the limit exist, we need the limit from the right to be the same as the limit as we approach -3 from the left. So we need the right-hand limit and the left-hand limit to match up. And we can go get these because, well, let me roll into that. So to be on, to approach -3 from the right-hand side means that we're going to be using to the right-hand side. I should be a little careful here with negatives. That means I'm using numbers like -2.9, right? Yeah, so that's this bottom one. So be a little careful here, that was wrong. And I'm going to go to this function, x plus 7. Okay, but x plus 7 is a line, and lines are continuous. So to evaluate this, I just get to drop in the number. I get 4. Okay, so now to approach -3 from the left-hand side, then that's something like -3.1, and that's this function up here. So now I'm on that top function, which is f at x. And f at x, let's write this out now that we need it. F at x is the square root of 25 minus x squared, which, as I mentioned, was this nice and continuous semicircle. So since it's continuous, then again, I can just drop in -3, and that turns out to be 4 also. Okay, so that's pretty tricky, but these two combine then say that the limit as we approach -3 of our function g, the piecewise defined function, not only exists, but it's equal to 4. Therefore, g is continuous at -3. All right, and then that's a lot of explaining, but that's what they want us to do, explain the answer. So let me just recap that again. The idea of continuity is that the value of your function exists, the limit as you approach that value exists, and furthermore, they're the same. All right, so I could say a little bit more now that I feel like it. You know, the first one would say that g at -3 exists, and it's this dot. And the second one would say that there's a limit, because as you ride this thing from the one side and ride this thing to the other, you're approaching the same height. So this would be the existence of g at -3, this place being -3. And this would be the limit as we approach -3 exists. But this wouldn't be saying that they're the same. Okay, so this is not continuous, and you can see that you have to lift up your pencil. So the minute that you take this dot and fill it in, wish I could do that. Okay, fine. As soon as you take that dot and drop it in there and fill it in, then you're forcing this last one to be true. Okay, so that's why you need all 3 cases. And then we just needed to go and show that, and they made this part more complicated. Okay, so let's go on to D, which they do, of course they know you have a calculator, but if they do something like this, which is free game, because they want to know that you can integrate, at least they want to know you can integrate by using the substitution method. Parts turns out to be not a B, but a BC topic for crazy reasons that I don't understand. So I just tacked on show all steps. Okay, so this is a review of a U sub. Why is it a U sub? Because the derivative of one part shows up somewhere else. That was our tool. All right, so here we go. Let U equal the interior one, 25 minus x squared. Notice I'm not grabbing the square root, just grabbing the simplest version that has a derivative that shows up, so that's this one. All right, so then I'll take the derivative of this side with respect to x and this side with respect to x. And so of course I can swap out this part as a u, but then I need that as a du, so that is y. We are solving for dx over here, swinging it over to the other side, and finally dividing off the negative 2x. Okay, so making this substitution, I now have the integral of x root u, and dx is turned into du over negative 2x. And if this doesn't happen, then you didn't do it right. Okay, so that's the built-in check. Now then, we've moved to u's, so those are not x's, those are just blanks. So we've moved to u's, so then I'm not carrying 0 to 5, right? I'm just sort of reminding myself that I'm going to need a back substitute in a little bit. Okay, so plucking out this negative 1/2 and changing this to u to the half so I can reverse power rule it, off I go. So let's see, this is now u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3, and that's evaluated from those little placeholders. So that's negative 1/3 u to the 3/2. U was 25 minus x squared. And that's running from, now I'm putting them back in since I did my back substituting. Okay, so by the fundamental theorem of calculus, I'm now dropping in the upper limit, which is 5. And then I'm going to subtract from that. Notice my little double negative, so I'm being careful. And then I'm going to subtract from that, dropping in 0. Okay, so this one zeroes out, bam, because you get 0 in there. That's a double negative for 1/3. And then that's 25 to the 3/2 power, which is, what is that? That's the square root of 25, 5 cubed, that's 125. So there we go, 125 thirds. I showed all my work. Okay, so that was pretty fast. I'm looking at my timer here. That was 18 minutes plus my preamble. So I did that pretty fast. Maybe that was what they consider a 15-minute problem. I'm not totally sure. Okay, but that was a nice all-encompassing problem. All-encompassing, not even close. But anyway, it did have a lot of parts. All right, so let's move on to the second problem. All right, here is the second problem. Please do it, and then at your convenience, come back and you can check your work and your logic by listening to me roll it through. And this is the last problem before you are on your own. It's the baby bird problem. So Papa Bird is leaving the nest. You're on your own, my little baby birds. Okay, here I go. This looks like a differential equation, I might add. All right, so just taking note of that at first glance, and of course then they start talking about the differential equation above. We've got an initial condition, but yeah, let my eyes not get too far ahead. Let me just back up and read it. Okay, so the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time 0, when the bird is first weighed, its weight is 20 grams. If B of t is the weight of the bird in grams at time t days after it is first weighed, then the derivative of B with respect to t is equal to 1/5 times the quantity 100 minus B, the weight of the bird. Okay, let me say a little bit to this. So it does say that the rate, this is the rate of change of the weight of the bird with respect to time, is proportional, so it's It's good. This is a constant of proportionality here, and it's proportional to the difference between the adult weight. So now I know the adult weight of the bird is 100 grams, and the current weight of the bird. So when the weight of the bird is small, okay, then this number is going to be pretty big, and the growth rate is going to be, well, I don't know, whatever 1/5 times that is. Okay, but let's say that's somehow a sizable number because B is super small. But as B gets bigger, so let's say it's up into like 90s or something, then 100 minus 90 isn't very big. And okay, so the idea is that the bird is growing faster when it's smaller than when it's closer to its actual adult weight. Okay, so all that makes sense, but I'm just thinking that through. Okay, so let's see. Let y equal b of t be the solution to the differential equation above, and the initial condition is b naught equals 20. Okay, so they said that. All right, part A. Is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Explain your reasoning. 40. That's what I was just talking about. The bigger this number is, the bigger that number is. This is the speed at which it's gaining weight, right? Okay, but we need to convince people of that. So I suppose we want to show this. We want to show that dB dt when b equals 40 is greater than dB dt when b equals 70. All right, so we can do that. We have a formula for this. It's just right up there. And that's 12. And then on this side we have 1/5 of 100 minus 70. So that's 30. A fifth of 30 is 6. Yeah, 12 is greater than 6. Done. Explain my answer. I guess I could explain my answer in words. I don't know that they want me to do it in words, but whatever, I'll do it. So what's my logic here? The larger the difference in adult weight and current weight, the larger the growth rate. I think I can get away with that. The larger the difference in adult weight and current weight, the larger the growth rate. All right, so this one with 40, that's a larger difference than that is over here. So this growth rate is going to be larger than that one. Okay, fine. A is done. Let's move on to B, which involves that picture. So let's get that picture just attached to that. And let's get sort of C off the picture so we can just concentrate on B here. Okay. Ooh, seems like we've seen a problem like this recently. Find the second derivative of B with respect to T in terms of B. Okay, so that's fine. Let's just think about that. That means our answer is going to have some B structures in it. And then we're going to use that to explain why the graph of B cannot resemble the following graph. Now that's kind of confusing. Let's just focus here on find d squared B dt squared, the second derivative of B. All right, well, let me start with the opening fact that dB dt was equal to 1/5, and then it was 100 minus B. All right, so then I'm going to take the derivative of this side with respect to B. No, sorry, with respect to T, sorry. And I'm going to take the derivative of this side with respect to T. And hopefully alarm bells are going off because you realize that you're differentiating with respect to T, but you have no T's. So let me just change colors and remind you that b is a function of t. That's defined in the setup. We don't know what that function is, but it is a t-like structure. As time changes, the weight of the bird changes. So b is a function of t. All right, so let's roll this out. Over here we have exactly what we're looking for, the second derivative of b. And then over here, we need to pluck out the constant. We can leave that constant there. And then we're going to take the derivative of 100 minus b, treating b like a single variable like it is, right? But it's really some t stuff, but treating it like a single variable, then we get a negative 1. But then by the chain rule, we need to multiply by its derivative. And then we can go and grab its derivative, which is 1/5 times 100 minus b. And then we have negative 1/25, 100 minus b. Okay, so I found the second derivative of b with respect to t. Now, I'm supposed to then use this to explain why this graph cannot resemble, why this graph is not the graph of b, why the graph of b cannot resemble this graph. Okay, whatever, either way you think about it. Well, now, second derivatives. When second derivatives are greater than 0, then that means you're on concave up. When second derivatives are less than 0, you are on concave down. Now then, the b values are the weights of the bird, and it looks like the weight of the bird can be between 20 and 100. At time 0, the weight of the bird was 20. The adult bird is 100, so this is my domain for b, which means that this is always positive, which means this thing is always negative. Therefore, b, the original function, is concave down everywhere. All right, so explain why the graph of b cannot resemble this one. B is concave down everywhere. So the graph is not b's graph because the graph is concave up for part of it. It's concave up right in there, right? This whole section here is concave up. All right, so that is my part B. Let's go on to C. And this is just the classic problem, and we'll have to roll this out. And it just is a lot of algebra usually, so I'm thinking that they're going to do this to us. All right, so use separation of variables to find the particular solution since we do have an initial condition. All right, so let's remind you of what's going on here. We've got a differential equation, which is as follows. And we want to go find the function b of t with the initial condition b of 0 equals 20 using separation of variables. Okay, so that's actually a nice big hint. So here we go, separating some variables. I'm going to bring over here the dt. So I want all my t stuff over here and all my b stuff over there. So now I'm going to divide off And you could divide off this whole thing, but I'm sort of seeing that that's going to be a little more annoying than if I leave the 1/5 over here. It can be made to work either way, but I'm going to do it this way. And okay, so now it's time to integrate throughout. So I'm going to integrate this one and integrate that one. This one is with respect to b. Okay, so if you think about this as a function, the integral of 1 over f of b is the natural log of that function. But then we need to divide by, because this is linear, otherwise it would be really hard. But we need to then divide by that guy's derivative, which is -1. Okay, now don't be thinking like you have to have this as earlier, like thinking this is a function of t, because after all, we are going with respect to b now, so you don't have to worry about that. And then over here, we get 1/5 t. Now, it's true, plus c, but you have to just write plus c somewhere. All right, that's a good reminder. But now we need to go find c. So we have this initial condition that b of 0 is 20. Therefore, we have this point. You put in 20, or you put in 0 for t, and you get out 20 for b. Times 0, the bird's weight was 20. Okay, so let's do that. I'm going to bring this negative up, and I have the natural log of 100 minus 20, and then over here I get c. I'll write 0 plus c just in case you're watching this carefully. That's just good showing of the steps. Okay, so now I know c. So I'm going to take, because I think I'm going to need a bunch of room here, and I have my formula, but I need to solve for b. So what my formula is the natural log of 100 minus b. Just make sure no mistakes. Negative natural log of 100 minus b equals 1/5 t plus c, which I just found to be negative natural log of 80. And now it's time to solve for b. So swinging the negative sign over there, well, I'm just going to, I'll just throw the negative sign in there. That's fine. Nothing fancy. Okay, so now I'm going to each side, right? Use base e. And 100 minus b now, so I'm getting there. And then it's e to the 1/5 t plus natural log of 80. All right, so let's see. Minus 100 kills off that one. And then getting rid of the negative, I suppose, switches the places on these. And whether they would accept this answer, I suppose they would, but I can make it a little bit better, so let's do that. This, by the rules of exponents, is e to the negative 1/5 t times e to the natural log of 80. Certainly you're more used to the rule where you are multiplying common bases, so you add the powers, but the powers were already added, so now I'm breaking it apart because this one's nice. All right, so this is the final answer, and it is 100 minus 80, that's 80, e to the negative 1/5 t. All right, I think I answered the question. Use separation of variables to find b of t. Ta-da. Notice it's with respect to t, so I'm all good there. And okay, that's a wrap, everybody. Let me know what you need me to do. I'm happy to help. And once again, good luck. All right, take care.